So as promised, we're going to do a little bit of review here today. I don't like to throw a whole lot of new material on you your first day back from vacation, but I do want to make sure you guys understand the basics. And to do that, I want to review a little bit about how numbers work, just to remind you, just because I do things a little differently. When we deal with numbers, when we add or subtract, what are the things we need to know? Before we can add or subtract, what must we have? Well, numbers, yes. But remember, numbers have two parts. All numbers have a count and a name. And in terms of those counts and names, what must we have before we can add or subtract? Must have same name. Like 5 inches, we can add to 4 inches to get 9 inches because they have the same name. Or 3 pounds can be added to 7 pounds to get 10 pounds because they have the same name. 3/7 can be added to 2/7 to get 5/7 because they have the same name. Scientific notation was the same way. We could add 5.1 times 10 to the third plus 2.3 times 10 to the third because they have the same name. 10 to the third is their names. That's just going to give us 7.4 times 10 to the third. Look familiar? So to add or subtract numbers, must have the same name, whether it's the same label, same unit, common denominator, same index, and a power for our scientific notation. Now, once we have the same name and we begin to add, the other thing is in the process of addition, what happens to the names? They stay the same. We keep the same name. Because we have to start with the same name because we're going to keep that same name. So we have to have the same name for the two numbers to begin with, otherwise which one do we keep? So those are two big things for addition and subtraction. Multiplication and division, do we need the same name? No, we do not. We can multiply 5 feet times 3 pounds and get 15 foot-pounds. We can multiply 3/7 times 2/5. 3 times 5 is 6. 7 times 5 is 35. We don't have to have the common denominator. And Dustin said it there because when we multiply or divide, we're going to combine the names. Multiplying feet times pounds makes foot-pounds. 7ths times 5ths makes 35ths. And for addition and subtraction, I didn't really show the subtraction because it doesn't change much. But for the division, I'll show that here quick. We might have something like 8/25 divided by 2/5. Just like multiplication, remember we can divide the counts. 8 divided by 2 is 4, and also divide the names. 25 divided by 5 is 5, 4/5. Or we might have 27 inches squared divided by 9 inches. 27 divided by 9 is 3. Inches squared or square inches divided by inches is just inches. We divided the names. Combine the names. So how does that apply when we come to our algebraic numbers, the variables? The variable is the name. This is just like having 5 inches and 11 inches. Well, it's 5 x's and 11 x's. What do we get? 16x. We have the same name, so we combine the counts. 5 plus 11 makes 16, and we keep the same name. X and x stays x. So what's that going to become? 3x plus 8y. They don't have the same name. We can't combine them. No. Combine with any operation. Nope. 3x plus 8y. It stays that way. For adding or subtracting, we must have the same name. So we cannot combine those with addition or subtraction. Now 5x times 4x is going to be 5 times 4 is 20 x squared, because we also combine the names. X times x is x squared. Seven x times 3y. Well, we gotta do 7. Can we combine those? Yeah, with multiplication, we don't need the same name. So 7 times 3 is 21. Yep, xy. We also combine the name. Just like feet times pounds became foot pounds, x times y became xy. Remember these? Exponents, yes. Of course, remember x to the third was just 3 x's multiplied together. X to the 8th is 8 x's multiplied together. But when we multiply them, what do we get? X to the 11. Remember, when we're multiplying, the appearance, we can't say that we're really adding the powers. The appearance is that we're adding the powers. We're really multiplying, but it appears as though the powers are just getting added. And we can always use that as a shortcut. Y to the 7th times y to the 15th is going to become y to the 22nd. How about that one? Subtract them, so you get z to the 5th. So that's going to be what? Perfect. So how about this one? Let's do it like that. Why? Different bases. Yeah. The whole idea of combining the powers originates we have to have the same base of the exponent. So it has to be x and x, or y and y, or m and m, or z and z. How's about this? X to the 15th. How do we get that? Yeah, 3 times 5 is 15. So this is going to become e to the 44. Well, since we're having fun, I'm going to have you guys try one in your notes. No quiz yet. Just try one.
It's been a while. We just had one 3 weeks ago.
I wouldn't give you a quiz in your first half hour. Give me 6 more minutes.
If you're going to start that, you can skip it.
Try that one in your notes quick. So on this, the first thing we got to do, of course, we want to work inside the parentheses. 18 divided by 6 is 3. X to the 5th divided by x to the 3rd, x squared. Y to the 2nd divided by y to the 8th, y to the negative 6. We'll talk about that in a minute. Now to the 3rd power, you could just have it as over y to the 6th too, if you wanted to.
You can?
Yeah. It could look like this too at this point. Means the same thing. It's easier for me to see it like this in a single line, but you both of them, in fact, many textbooks demand you have it as positive exponents. Yeah. So now, the power of 3 here. 3 to the 3rd power is not 9, it is 27. 3 times 3 times 3 is 27. It's when we get to the exponents that we do multiplication. X squared to the 3rd power is x to the 6th. Then y to the negative 18, or that could be 27 x to the 6th over y to the 18. Either one of those would be correct. What does a negative power mean? X to the negative 4th. It is a decimal if it's a number. It actually makes it into decimal. What it really is a fraction. X to the negative 4th is, the negative power is a reciprocal. X to the negative 4th is the same as 1 over x to the positive 4th. Remember, if we look back, if we had 5 to the 4th power, that's 625. 5 to the 3rd power is 125. 5 squared is 25. 5 to the 1st power is 5. We had a pattern developing there. When we had our base of 5 and our exponents, when the power was reduced by 1, the answer was divided by 5, right? So when we go down to 5 to the 0, what's 5 to the 0 have to be? Not 0. If I divide by 5, it's 1. Anything to the power of 0 is 1. Now as we keep going with that, now 5 to the power of negative 1, I divide by 5 again, it's just 1 divided by 5 is 1/5. 5 to the negative 2 divided by 5 again, that'd be 1/25. 5 to the negative 3, that's 1 to the 1/25. And here's where, if you look closely, you'll notice the connection between the negative powers and the positive powers. 5 to the 3rd is 125. 5 to the negative 3rd is 1 over 125. 5 to the 2nd is 25. 5 to the negative 2nd is 1 over 25. What do you think 5 to the negative 4th is going to be? 1 over 625. The negative power is just a reciprocal. X to the negative 4th is just 1 over x to the 4th. That is why when we had that 1 over y to the 6th, you could write it as 1 y to the negative 6th. Either one. They mean the same thing. Right. Yeah, it'll approach 0 but never reach it. It's called an asymptote. Let's see here. Asymptote. Asymptote. Yeah. If you get into economics or quality control, even sometimes they call it asymptotic behavior, and that just means that as your certain conditions go either off to infinity or to 0, it approaches a certain value. And it's important when you get into like linear analysis and stuff like that. It's your actuarial work where you're trying to use numbers to predict things.
Do you guys do graphing on
the XY?
Yeah, where you have different.
Oh, we don't do like elliptical surfaces or anything like that. No. We basically graph lines and parabolas on a 2-dimensional flat surface. Yeah, we're not going to get into elliptical geometry or anything like that. I don't hate you guys that much. Well, You know, the whole argument about pi equals 3.14159, blah, 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 blah. That only applies to plane geometry, not on flat surfaces. If you deal with spherical geometry, on a sphere, pi is 3. But you got to remember that the diameter of a circle is not a straight line on a sphere. The diameter of a circle is an arc over the top of the surface of the sphere. We're so used to thinking of everything as being flat. And in reality, since we're working on small scales, you can approximate everything pretty much with a flat surface. So anyway, what is 8 to the power of 2/3? Now, first of all, some of you might be able to put that in your calculators. You should be able to. Yep. You have to use the ABC key for fractions to put it in as 2/3. But it'll go in there. Yep, 8 caret key, 8 caret 2, ABC3. Should get 4. Why? Not just because your calculator told you so. Why is that 4? Well, let's step back a little bit. What's that symbol mean?
Square root.
Square root. What is the square root of 4? 2, or there's another option, -2. Remember, -2 squared could also equal 4. And that square root is asking us what number squared equals this number. What's that? 4 to the power of 1/2. It's 2. How about the square root of 25? 5. We're just going to stick with the positive. We know there's a -5 there, but we don't really care at this point. What's 25 to the power of 1/2? Try it on your calculator. What's the square root of 81? 9. What's 81 to the power of 1/2? Do you see a pattern developing here?
That's square root. You do the half.
Yeah, the 1/2 power is the square root. I'm going to show you with my exponents. What's the square root of x to the 8th? X to the 4th. Why? Because x to the 4th squared, 4 times 2 is 8, x to the 8th. The other way I could turn x to the 8th into x to the 4th, x to the power 1/2, I multiply the powers. 8 times 1/2 is 4. So when I have a power like this, 25 to the 3/2, it's actually 2 separate problems combined into one. And there's actually a choice. I can either do 25 to the 3rd power and then to the 1/2, or 25 to the 3rd power and then square root it, or I can do 25 to the 1/2 first, in other words, the square root of 25, and then to the 3rd power. Either way, what's 25? What's the square root of 25, or 25 to the power 1/2? That's 5. 5 to the 3rd is 125. 25 to the 3rd power is 15,625. And the square root of that is 125. What do you think? Slowly sinking back in. Well, let's take a step back to negatives. -7 squared. If I square a negative number, positive or negative? A negative times a negative should always be a positive. Punch that into your calculator once. See what it says. No, it's positive. What did you have to do, though, to make it give you that positive answer? You had to put it in parentheses, just like I did here. I have parentheses around the -7. When you enter that in your calculator, some calculators do it correctly without the parentheses. Most calculators have to have those parentheses in order to do it correctly. Yeah. What it does, if the parentheses aren't in there, it squares the 7 first, and then it makes it negative. Order of operations says the power happens before a negative. -7 to the third power, -343. You got it. Because it's an odd power. Very good. An even power, no matter what you're starting with, will always be positive because the negatives cancel out, basically. An odd power can give you a negative result. Now, the flip side of that, we've talked about square roots. What's the square root of a -64? Calculator is going to give you error. Because there's no number that I can square and get a negative result. Any number squared will be positive. So there's nothing that I can square to give me a -64. So I cannot take the square root of a negative number. However, what's that symbol mean? Third root. What that is asking me is what number to the third power is the number inside the symbol. In this case, a -125. That is a -5. An odd root we can do because an odd power is capable of giving us a negative result. Does that make sense? Coming back to us slowly? Okay. For tomorrow, you have one problem of homework. This is it. For tomorrow, that is your homework.
Immediately I thought you were going to write a second line.
I thought that was going to be
It's going to be a fraction? No, I'm not quite that mean. Not on the first day back.
That's my mistake.
Speaking of Wednesday, by the way, there's a good chance I won't be here for this class on Wednesday. We'll let you know tomorrow.
Oh, wow.
You're a good guy.
I have a dentist appointment.
Oh, yeah?